Good afternoon, colleagues. My name is Vladislav, and today I'm going to present the paper that describes domain transferable method for named entity recognition task. So named entity recognition is a fundamental task in natural language processing and information extraction. So it has been widely used as a standalone tool or an essential component in a variety of applications, such as question answering, dialogue assistance, and knowledge graphs development. However, training reliable models requires a large amount of labeled data, which is expensive to obtain, particularly in specialized domains, since these require domain expertise. So English has always been the focus of the research, specifically in the field of NER. Thus, there are plenty of both structured and unstructured resources for the language, which are publicly available, such as datasets, knowledge graphs, pre-trained language models, or pre-trained downstream models. So however, there are no such resources for the Russian language, which makes the task difficult to solve. So we investigate a setting when no domain-specific supervision is available and no annotation resources are available. So we proceed from the assumption that a model can learn from another model and domain-specific texts can be annotated without human supervision, using only constructed vocabulary. So we explored the method that to construct a domain-specific data set for NER without human supervision, and then use it to train our own specific NER model for extraction of knowledge graphs entities and in the downstream task of the question answering. So we first construct the entity vocabulary using Wikipedia, category graph, and seed words for category names. We then implement a morphology-based algorithm to automatically annotate texts. We also fine-tune BERT model on a publicly available general domain dataset, Wikiner. We then automatically annotate all the collected text to construct the domain-specific dataset. And finally, we tune the target domain-specific BERT-based model. So we conduct the experiments in the domain of Russian history, which is represented by both generic entities and domain-specific entities. Data collection pipeline consists of two stages, construction of the vocabulary and collection of the domain-specific texts. So we used Wikipedia API to retrieve lists of titles of Wikipedia articles related to the domain of Russian history. So we traversed the graph over a set of seed categories and collected a text of the corresponding article, a summary, a list of categories, and a list of interlinks in the article. Each interlink and Wikipedia title are considered to be named entities and added to the vocabulary. We then additionally filtered the resulted vocabulary based on the interlink frequency and seed words such as war, battle, and etc. In the second stage, we constructed a domain-specific corpus that consists of texts from publicly available resources, such as books about Russian history, educational books, documentaries, and series of lectures. So the size of the corpus is about 5 million tokens. Consider an example of the named entities in the resulted vocabulary. So the vocabulary includes generic entities such as historical figures, names of battles, wars, and cultural properties, and also domain-specific entities such as historical terms, concepts, and phenomena. An important note should be made that the quality of the vocabulary depends on the depth of the Wikipedia graph traversal due to a number of ambiguous titles and a large degree of cross-reference in the articles. To obtain annotations on the domain entities, we implemented the algorithm that is closely related to the Sesama method. So this work proposes assembly of general domain net dataset called Sesama, using the Wikipedia as a source of named entities and their semantic types, and Wikipedia as a document collection. A basic idea is to detect mentions of the Wikipedia entities in a Wikipedia text based on the exact match. So each entity mention is tagged then with its corresponding semantic type from the Wikipedia. So we adapt the method to the Russian language. So we use a Russian morphological analyzer Pomorphy 2 to identify mentions of entities from our vocabulary in each text from the domain document collection based on the exact match of the lemmas. So we use the inside-outside beginning scheme, tagging scheme. However, we don't have the information about semantic types such as the Wikipedia, so we tag each entity with the miscellaneous tokens. So note that here we can use knowledge graph, for example, Wikidata, and map the instance of the entity like city to the semantic label location. We also can manually annotate our dictionary once and then simply replace the entity, the exact match, with its corresponding semantic labels. So we also treat this kind of information as a source of the domain knowledge. So we then use Rubert model fine-tuned on Wikiner for the Russian language to obtain general domain annotation. So Rubert is a monolingual BERT model for the Russian language, which outperforms multilingual BERT over a number of NLP tasks for the Russian language. We use this architecture for both the general domain model and the final model. So therefore, each text from the corpus has two annotations. So one with the BERT model and another with the morphology-based algorithm. So the next step is to unify the obtained annotations. If an entity mention is annotated by both Rubert model and the morphology-based algorithm, we prefer the Rubert general annotation to be to the morphology-based one. This allows to preserve relevant semantic labels for generic entities. The unification procedure is illustrated in the figure. So after the procedure, we discarded duplicates and samples that are labeled only with the outside token. The size of the filtered dataset is 160,000 samples. We also combine the Wikinet dataset with the constructed one to obtain the final dataset. In our experiment, we trained 3 BERT-based models on the constructed dataset. So the first one is the BERT Original, which is a multilingual BERT model. The second one is a Rubert Original, which is a monolingual BERT model for the Russian language. And the last one is Rubert Adapted model. What does adapted mean? It means that we fine-tune the Rubert model on the collected domain-specific documents before training on the downstream task. So this is a common trick to improve the performance of the models. And it's proved in other works that even such adaptation of the language model, even on a small amount of labeled data, can improve the performance. So knowing that the annotation procedure, the annotation samples in the collected data set may contain automatic annotations errors or be inconsistent. We also manually annotated extra 2,000 samples from the Unified State History exam. So the additional test set allows to evaluate the performance of the models more reliably, disregarding this potential deficiency. So the models are evaluated over a full inventory of semantic labels. We computed the metrics by taking the average over the weighted number of instances. So in our work, we aim at extracting mentions of knowledge graph entities from texts. So we are not interested in their semantic types, but this can be a useful feature for the ranking model. So the proposed method to train a domain-specific model has received a satisfactory performance without human effort. So the availability of Wikipedia in multiple languages and versatility of the Wikipedia graph may potentially allow for the transferability to new domains and across languages. However, a number of drawbacks need to be solved for better performance and generalization of the method. So the first one is that the constructed vocabulary is not guaranteed to be free of noise. The main reason for irrelevant entities is a large degree of cross-reference in Wikipedia article. This may cause redundant label predictions or incomplete predictions in the inference step. So the drawbacks can be alleviated by extracting mentions of entities using a curated list of Wikipedia sections, additional vocabulary filtering, or validation by annotators. Also, the constructed entity vocabulary suffers from incompleteness. So this may be due to the following reasons. First of all, not all of the interlinks and entity aliases are highlighted in the Wikipedia article, so they cannot be extracted during the collection procedure. Second, an interlink always refers to one Wikipedia title or the same surface form of the named entity in the vocabulary. So this results in a low lexical variability of the entity vocabulary. Despite a rich variety of domains covered in Wikipedia, domain-specific knowledge may not be sufficiently represented in the document collection, as well as similar publicly available resources. So this necessitates the extra data mining for the model to learn relevant context. Another problem is lemmatization quality. In some cases, incorrect lemmas are obtained due to word ambiguity and the rich inflectional morphology of Russian. Besides, the morphology-based algorithm only partially covers the inventory of semantic labels. So this also leads to annotation inconsistency. Although the majority of such cases are solved during the unification procedure, the remaining part still leads to the inconsistency. So the model may get confused during the training or the inference steps. However, we believe that the method can be applied in domain-oriented areas, such as processing legal documents, educational dialogue systems, and QA systems over knowledge graphs, specifically when there are no annotation resources or no supervision available. For languages such as English or some agglutinative languages, the method may potentially be transferred with a better performance, specifically due to availability of the structured and unstructured resources. So the steps of the method can be modified depending on the data available. The method is based on the semi-supervised approach. Specifically, a document collection can be automatically annotated using natural language pre-processing tools and domain-specific entity vocabulary, which can be constructed from scratch. We assume that neural models can learn from each other. So pre-trained language models can be used for training an R model that is aware of both external and domain knowledge. We empirically show that both-based models trained over the method receive satisfactory performance without human effort. However, a number of drawbacks need to be solved to gain the performance, so future work is to be dedicated to the quality improvement and exploring the transferability of the methods across multiple domains and languages. So the latter can be obtained thanks to versatility of Wikipedia. So thank you for your attention. I'll be glad to answer your questions.